Imagine a piece of software that can download source code directly to a microcontroller, right? But it does it faster than standard hardware tools, can even flash a precompiled binary.
Which is just wild to think about.
It really is. Today, we're jumping into this deep dive on a fascinating piece of software called Fastforth.
Yeah, and Fastforth is, well, it's essentially a programming landscape that's been stripped down to the absolute bare atoms.
Exactly. It's designed specifically for the Texas Instruments MSP430FR family of microcontrollers. And, our mission today is to really unpack how a system with a minimalistic kernel size of just 4.75 kilobytes,
Right, which is tiny.
just microscopic,
Yeah.
and fully loaded, it's only 10 kilobytes. But we're going to look at how it achieves these crazy effective interpreter speeds of 800 kilobyte.
Yeah, I mean, it's processing incoming text literally faster than modern industry tools can blast raw ones and zeros over a wire.
Which, completely upends the modern expectation of embedded development.
Oh, totally. Because we're so accustomed to building these massive software skyscrapers,
Yeah.
You've got gigabytes of C compilers, these huge hardware abstraction layers, or HALs, and then entire operating systems sitting between the developer and the actual silicon.
And Fastforth basically just demolishes the entire skyscraper.
It does. You're sitting directly on the bedrock. You're talking to the processor in its native tongue.
And doing it entirely on the chip itself, which is the crazy part. Because for anyone used to the standard workflow, right, you typically write your C code on this beefy, powerful desktop computer.
Right.
Then you compile it into this massive, monolithic binary file, and you flash the whole thing over to the microcontroller.
Yeah, and if you want to change, like, a single variable, say you just want to tweak the blink rate of an LED by a few milliseconds.
So to recompile the entire massive binary and reflash it all over again.
Exactly. It's a huge bottleneck.
Yeah.
But Fastforth is an interactive, stack-based environment, and it lives entirely inside the microcontroller's memory.
Right, so you just type a command on your computer's terminal, it goes over the wire, and the tiny processor it executes it instantly.
You're literally building the application live, word by word.
But, taking a step back for you listeners who might be new to this specific architecture, it forces a completely different mindset.
It really does. I mean, I've spent the bulk of my career writing C and assembly for ARM processors, and standard MSP430s.
Right.
And honestly, committing to a highly specific kind of idiosyncratic toolchain like Fastforth, it means walking away from the massive, ubiquitous, heavily supported C-based firmware ecosystems.
You're losing a lot of safety nets.
You really are. You lose the massive libraries, the corporate support, all those easy Stack Overflow answers.
So you really have to ask if the cleverness of the design actually justifies that kind of isolation.
Exactly. Like, as a pragmatic developer, I have to wonder, is the lock-in actually worth it when ARM Cortex M0 Plus chips are basically a dime a dozen these days?
And that is exactly the tension we're going to explore in this deep dive. Because to even begin to judge its practicality, we have to look at the mechanisms making that 800 kilobaud speed possible.
Right. Because it doesn't get that speed by accident.
No, not at all. It gets it through uncompromising bare metal optimization at the absolute lowest architectural level.
Yeah, so let's look at the heartbeat of this language, which is the threading model.
Okay, lay it out for us.
So in Forth, your program isn't just a massive blob of machine code like you'd get from a C compiler. It's essentially just a list of pointers.
Like memory addresses.
Right, pointers to other small routines, which then point to other routines, cascading all the way down until it finally hits the Silicon's native machine code.
And how the engine navigates from one pointer to the next that basically dictates the execution speed of the entire system, right?
Exactly. And Fastforth uses a method called direct threaded code, specifically a variant called DTC2.
Okay, so break that down for us. Why DTC2?
Well, when you build a Forth system, you have to choose how those pointers resolve. Indirect threaded code, or ITC, is the classic approach.
Right, the traditional way.
Yeah, and it's incredibly compact, memory-wise, but it's slow because every single execution requires a double memory lookup.
Okay, so what's the alternative?
The other extreme is subroutine threaded code, STC, that just lays down raw machine-level call instructions.
Which I'm guessing is fast.
It's blazingly fast,
Yeah.
but it completely bloats the memory footprint because a call instruction on the MSP430 takes multiple bytes for every single word.
Ah, and when we only have 4 kilobytes of dictionary space, we can't afford that bloat.
Exactly. So DTC2 is the compromise. It perfectly balances execution speed with those severe memory constraints.
How does it actually work in practice?
Basically, the system evaluates a pointer, If it points to high-level Forth code, it jumps into a handler to process it. But if it points to raw assembly, it just executes it natively right there.
That's super clever.
Yeah.
But the engine driving this entire train is that tiny piece of assembly called the next routine, right?
Yes, the next routine. Every single time a Forth word finishes its job, it essentially has to ask, okay, where do I go next?
And in Fastforth, that next routine is literally exactly one assembly instruction.
One instruction, MOV at IP plus OPC.
So it moves whatever the instruction pointer is currently looking at, increments that pointer to the next address, and shoves the result directly into the program counter.
You got it. And here's why this matters for the MSP430 specifically. That single instruction takes exactly 4 clock cycles.
Which sounds like a lot if you're thinking about a desktop PC.
Right, 4 cycles is an eternity on a 3 gigahertz desktop processor. But on a 16 megahertz low-power microcontroller, it is practically instantaneous.
And we should compare that to a modern ARM Cortex chip because it really highlights the difference.
Oh, absolutely. If you try to do a complex dynamic branch like that on an ARM chip, you might trigger a pipeline flush.
Because ARM chips try to guess what code is coming next, right?
Yeah.
Speculative execution.
Exactly. The processor guesses you were going one way, but you went the other. And suddenly you waste a dozen clock cycles just dumping the pipeline and reloading the correct instructions.
But the MSP430 doesn't do that.
No, it uses a simpler von Neumann architecture. There's no complex speculative execution pipeline to flush. That 4-cycle NetXT routine is perfectly deterministic.
It's guaranteed to be exactly 4 cycles every single time.
Every single time. But pulling off that continuous 4-cycle loop requires a massive sacrifice in how the processor's internal memory is managed.
Right, the register map. This is where it gets really intense.
Yeah, so registers are the fastest possible memory on the chip. They sit directly inside the ALU, the arithmetic logic unit.
And the MSP430 only has 16 of them total.
Only 16. And Fastforth makes this incredibly aggressive choice to permanently dedicate register R14 to the top of stack.
I was actually looking at how it handles stack math, and it's fascinating. Because Forth is a stack-based language, obviously.
Yeah.
You push numbers onto a stack to work with them.
Right.
Normally, that stack lives out in the regular RAM, which is, relatively slow to access.
Yeah, you have to wait for the memory bus.
But by pinning the absolute top item of that stack permanently into register R14 any math operation, like adding, bit shifting, XORing, it all happens at 0 wait states.
Exactly. It's instantly available to the CPU core. 0 delay.
But wait, if we use R14 for the top of stack, aren't we robbing Peter to pay Paul? Like, what happens when we need that register in regular assembly?
That is the exact problem. The issue with pinning registers is starvation.
Right.
Think about it. Register R0 is the program counter. R1 is the stack pointer. R2 and R3 are hardware constant generators.
So they're already spoken for.
Exactly. Now, if you permanently lock down R14 for the top of stack, and then you also lock down R4 through R7 as dedicated handlers for Forth behaviors like doubtful for colon definitions or diacon for constants.
The developer is suddenly running out of breathing room really fast.
Very fast. If I need to drop down and write a highly complex hardware critical assembly routine, I need registers to shuffle my data around.
Right, you need workspace.
But if the operating system is hogging half the register file, my custom assembly code just becomes horribly bottlenecked by constant memory swaps. I'd have to keep pushing things out to slow RAM just to free up a register.
Yeah, it's like having a high-performance sports car, right?
Yeah.
But half the gears in the transmission are permanently welded into place because the onboard computer needs them for itself.
That's a perfect analogy. But thankfully, the MSP430FR architecture actually provides a built-in escape hatch for this exact problem.
The PSHM and POPM instructions.
Yes. Push multiple and pop multiple.
These are so cool.
They are a massive advantage for context switching. In older microcontrollers, if you wanted to save, say, 5 registers to the stack so you could use them temporarily,
You had to write 5 separate PUSH instructions.
Right. PUSHR4, PUSHR5, PUSHR6, it consumes a ton of execution time and it blows the code size.
But with Fastforth, you just use POSHM Tech6 IP. And in a single clock cycle, the processor sweeps 6 critical registers, including the instruction pointer and those locked system registers, and just dumps them all onto the return stack.
In one cycle. you instantly free up the entire register file.
Which is amazing. So you run your complex, heavy-duty assembly routine using every register you want.
Exactly. And when you're done, a single POPM instruction sweeps them all back perfectly into place. It completely mitigates the starvation issue we were just talking about.
That's brilliant. And, earlier you mentioned registers R2 and R3.
Oh, the constant generators, yeah.
This is one of the most brilliant quirks of Texas Instruments silicon, in my opinion.
It's so weird, but so smart.
The hardware engineers actually hardwired those two registers to act as constant generators. So depending on how you address them, the hardware it just manifests the numbers negative 1, 0, 1, 2, 4, 8, literally out of thin air.
It sounds like a magic trick.
It really does.
But the memory savings are very real. Think about it. If your code needs to check if a sensor value is 0, right?
Yeah.
A standard C compiler has to waste 16 bits of physical memory just to store the literal number 0000.
Just to have the 0 available to check against.
Exactly. But Fastforth just points at register R3. The hardware intercepts the call, and it just feeds a 0 directly into the ALU. No memory lookup required at all.
And when you multiply that memory saving across an entire operating system, the dictionary space savings are just huge.
It all compounds, The 4-cycle NNXT routine, the R14 top of stack, the PSHM context switching, and these constant generators. This is exactly how you fit an entire interactive operating system and a compiler into 4.75 kilobytes.
It's mind-blowing when you compare that directly to a standard C-based embedded framework.
Oh, it's night and day.
Like, the source material explicitly nods to those bloated STM32 HALs. If I want to initialize a simple serial port in C, the hardware abstraction layer might pull in 20 kilobytes of generic clock configuration structures, struct definitions, error handling wrappers.
Let me turn on when you worked.
Exactly. I kind of look at it like a real estate analogy.
Yeah.
A standard C framework is like this massive, fully pre-furnished mansion. It's safe. It has everything you could ever need. It handles every possible edge case. But if you only ever use one single room in that massive mansion, the overhead is absurd. You're paying to heat and cool 100 empty rooms.
Yeah, that's exactly what C development on small ships feels like.
Whereas Fastforth is like a custom-built tiny home. Every single inch is completely functional, and there's 0 wasted space.
I like that. But because we've stripped away all that massive infrastructure and committed to this hyper-optimized DTC2 model, we don't have room for a standard, heavy compiler toolchain on the chip.
No, we definitely don't.
We have to be able to compile new code locally on the metal, and this forces Fastforth into what is easily its most controversial design choice.
The integrated assembler syntax.
Right, this is where it gets really heated in the Forth community.
So if you're writing Forth on the chip, eventually you need to drop down and write raw assembly for a specific hardware task, right? Like wiggling a GPIO pin.
Always. You inevitably hit the metal.
So Fastforth includes a built-in, label-free, 2-pass assembler to do this. But it breaks a fundamental rule of the Forth ecosystem.
A massive rule.
Because standard Forth assemblers, whether you're using G-Forth, Swift-Forth, or even most embedded variants, they use reverse Polish notation, postfix.
Yes. The standard way to write assembly in Forth is to push the operands onto the data stack first, and then call the assembly mnemonic to consume them.
Right.
So if you want to move the number 5 into register R4, in standard Forth, you write 5 #R4 MOV.
Which is backwards from how normal assembly looks.
Exactly. And Fastforth throws that entirely out the window. It uses native Texas Instruments assembly syntax.
So you just write MOV racetrack 5 R4.
Right. The exact string you would see if you opened up the official TI family user's guide.
But from a language ecosystem standpoint, isn't this a dangerous fracture?
Oh, it's a huge fracture. Every seasoned Forth programmer relies on the simplicity of postfix assemblers.
Because there's a historical reason they do it that way.
Right, exactly. The historical reason reverse polish assemblers exist in Forth is because they are computationally trivial to implement. Well, the numbers just sit on the stack. And the word MOV is just a standard Forth definition that mathematically combines those numbers into a binary opcode and writes it directly to memory.
It doesn't have to parse text.
Right. But by forcing native TI syntax, Fastforth now has to include a dedicated text parsing engine on the chip.
Which takes up precious space.
Yes. It has to scan the line of code, look for the comma separating the arguments, parse the pound sign for the immediate value, and mathematically resolve the addressing modes.
So you're talking about all those parsing engine routines like init and skip effects, jumping to param 1 and param 2,
Yeah.
setting a ton of complexity.
Massive complexity. And it limits extensibility.
Really? How?
Well, standard Forth assemblers allow you to create custom addressing modes very easily because everything is just a normal Forth word. You just write a new word.
Ah, I see.
But Fastforth's hard-coded parsing engine locks you into its specific hard-coded interpretation of the text.
Okay, I hear you. But playing devil's advocate here, I actually think this is the smartest decision the author made.
Really? Why?
Think about the friction of adopting a new tool. If you are an embedded C developer and you're transitioning to this weird new environment, you probably already know the MSP 430 architecture.
Sure, you've read the 1,000-page datasheet.
Exactly. You know exactly what MOV's Tag 5R4 does intimately. If you decide to try Fastforth, and suddenly you have to mentally translate every single familiar instruction into backwards reverse polish notation,
You're going to quit.
you're going to close the terminal and go right back to C.
Yeah, that's a fair point. It prioritizes the hardware documentation over the language purity.
Exactly. It completely eliminates that mental translation step for a newcomer who is already familiar with the silicon.
And to be fair, it manages to do this while still avoiding the classic RAM traps of traditional assemblers.
Oh, the label system.
Uh-huh.
We have to talk about the label
That's
system.
so clever. Normally, if you write assembly and you need to loop back to a specific spot, you write a text label, right? Like jump to loop start.
Right, and then the assembler has to figure out where loop start actually is.
Exactly. It has to build a massive symbol table in the RAM, storing the memory address of every single label string you typed. Loop start is at address 0 by 4000.
And on a chip with maybe 2 kilobytes of RAM, a symbol table will exhaust your memory almost instantly.
Instantly. You'd run out of RAM after a dozen labels.
But Fastforth completely removes label names. It uses a generic system of backward and forward branches.
Right, the BW and FW words.
Yeah. BW1 through BW3 for jumping backward, and FW1 through FW3 for jumping forward. It basically gives you 3 levels of nesting without any names.
Because these are generic positional markers that are resolved during the assembler's second pass, there is no symbol table at all.
The memory overhead for labels literally drops to 0.
It's brilliant, and it handles the complex two-pass encoding perfectly, especially on the larger MSP 430X chips, like the FR5994.
Oh, the ones with the massive 20-bit address space.
Right. Handling a 1 megabyte address space requires complex extended instructions like MOVX and CALA.
And Fastforth just handles it.
Yeah, it conditionally compiles a 20-bit extended assembler. It adds maybe 500 bytes to the kernel, but it perfectly calculates those complex opcode offsets without needing a single label table.
Okay, and here's my skeptical pushback. The danger of trying to make assembly syntax look friendly and intuitive is the massive footgun it creates with control flow.
Oh, the if then problem.
Yes,
Yeah.
because Fastforth includes branch constructs native to the assembler for things like if then and begin until.
Right.
The problem is, those are the exact same English words used for high-level Forth control flow.
And this is where developers will absolutely crash their systems.
So if I'm a developer and I am deep in the zone, right, I'm writing an assembly routine, and I type if to check a register flag, but I forgot to tell the compiler that I'm in assembly mode what actually happens.
It's a complete disaster. The system simply assumes you want the high-level Forth if statement.
Oh, no.
It grabs the high-level compilation semantics for if and violently inserts those pointers directly into your low-level machine code stream.
So the processor will eventually hit those high-level pointers.
And misinterpret them as raw opcodes. It'll trigger a hard fault or send the instruction pointer spiraling into random memory.
That sounds like a debugging nightmare.
It really is. The only safety net is the context stack. The assembler's version of if is actually hidden in a separate assembler vocabulary.
Okay.
So it's only visible to the compiler if the assembler word set is the actively searched context. If you haven't properly switched modes, the compiler just blindly trusts you and compiles the wrong if.
Wow. The danger of mixing up your modes is severe.
It is, but the irony here, the beautiful irony, is that this exact danger, the blending of high-level Forth and low-level assembly, is actually the foundation for Fastforth's absolute greatest superpower.
Oh, the crown jewel of the system.
Yes.
The ability to seamlessly mix them midstream.
It's incredible, because normally a definition is either purely high-level Forth, like a standard colon definition, or it's purely low-level assembly. They live in separate blocks.
Right. And if your high-level code needs to do something fast, it has to execute a full call command to the assembly block.
Which means you pay the execution overhead of jumping to a new location in memory, setting up the return stack, and then returning.
But Fastforth gives you HI2 low, and LO2HI, high to low and low to high.
Yeah, and it fundamentally changes how you structure code. You can open a standard high-level fourth definition, do some basic math on the stack, and then instantly drop down into bare metal machine code to, say, toggle a GPIO pin with exact microsecond timing.
And then just pop right back out.
Instantly pop back out to high-level fourth to format a string for the display, all without ever leaving the definition and without paying the overhead of a standard function call.
I like to map this out mechanically for people because it really helps me understand it. I think of it like a manual transmission in a car.
Okay, I like that.
The compiler is the clutch. When you are writing high-level fourth, the engine is engaged and it's chasing pointers. But then you type the word hi2lo. You step on the clutch.
Right. And the compiler intercepts that hi2lo command and executes a very specific sequence. First, it lays down a pointer called nextod.
And what does that do?
This is the exact signal to the fourth engine to stop pointer chasing, because it tells the engine that the very next byte in memory is raw, executable machine code.
So the clutch is depressed. The system state variable actually drops from -1, which means compile mode, down to 0, which means interpret mode.
Exactly. And the assembler vocabulary is suddenly swapped into the search order. Now we can slam the raw gears together. We write our MOV instructions or bitwise hardware toggles.
And that assembler parsing engine we talked about earlier, it translates those directly into opcodes, laying them sequentially into memory immediately following that nextad marker.
And when the code actually runs, the processor will literally just fall straight through the nextad instruction and execute your custom machine code at full native silicon speed. Zero overhead.
It's like a bilingual speaker switching seamlessly between English, high-level fourth, and Mandarin, the low-level assembly, right in the middle of a sentence.
Yeah.
And the processor, perfectly understands both.
Exactly. But when we are done speaking Mandarin, we need to re-engage the transmission.
Right. We type LO2HI.
And the system compiles an explicit assembly instruction. Call rdocall. This tells the CPU, hey, we are done executing raw opcodes. Jump back into the fourth engine's inner loop.
The system state shifts back to -1, the high-level vocabulary is restored, and you let off the clutch. You are back to compiling fourth pointers.
It automatically builds the exact architectural scaffolding you need on either side of the transition.
And it gets even better with something called HD encode hidden code.
Ah, yes.
Yeah.
HD encode solves the namespace pollution problem.
Explain that for us.
So if you are writing dozens of these highly optimized mixed-mode routines, you often need tiny helper macros, little snippets of assembly that you reuse frequently.
Like a specific delay loop or something.
Right. But you don't want those polluting the global fourth dictionary, where they might accidentally be called from high-level code and crash the system.
So Fastforth lets you define them using lowercase names.
Which is brilliant because the standard fourth find algorithm rigidly expects uppercase strings. Any word defined in lowercase is practically invisible to the high-level system.
They just become these private inline macros.
Exactly. But when you are inside a hi2lo low-level block, the assembler can see them. You can call these hidden helpers directly.
It keeps the public dictionary perfectly clean, while giving your low-level hardware routines this rich, accessible library of highly tuned microfunctions.
It's an incredibly elegant, hyper-optimized system for mixing logic and bare metal.
It really is. But the reality of embedded hardware is that it doesn't just live on a desk, right?
No, usually it lives in a field running on a coin cell battery or a tiny solar panel.
Exactly. So how do we actually interact with a system like this without instantly draining that tiny battery? Because microcontrollers use deep sleep states to survive.
Right, and the MSP430FR is famous for low power mode 4, or LPM4.
This is the deepest sleep state.
Yeah. In this state, the CPU is completely off, the main clocks are off, the chip is essentially dead, drawing sub-microamp current. You could literally run it for a decade on a standard battery.
But Forth is an interactive language. It requires a terminal that has to sit there waiting for you to type a character on your keyboard.
Which presents a huge physical problem. Traditionally, you use a UART, a universal asynchronous receiver transmitter, to talk to the PC.
But a standard UART is asynchronous, meaning there is no shared clock line between the PC and the chip.
Exactly. So the receiver on the chip has to constantly sample the line, waiting for the voltage to drop, which indicates a start bit.
And keeping that UART's high-speed sampling clock running consumes continuous power.
You simply cannot maintain LPM4 deep sleep if your UART is active. The physics of the silicon forbid it.
So the Fastforth architecture does something radical. It completely abandons the UART on the target device.
Just throws it out.
It moves the entire terminal interface over to the I2C bus, the inter-integrated circuit bus.
Which is a synchronous protocol. I2C has a dedicated clock line, SCL, and a data line, SDA.
And this is where the hardware hack is just beautiful, because the master device, the PC side, controls the clock line.
Right.
This means the target microcontroller can configure its I2C peripheral as a slave and immediately drop into LPM4 deep sleep.
It requires absolutely zero power to listen because the hardware address decoder on the I2C peripheral is entirely passive.
That is so cool. So when the master decides to send a character, what happens?
It pulls the clock line low and sends the slave's specific 7-bit hardware address over the wire. And the instant that address match occurs in the passive silicon, it triggers a hardware interrupt that just jolts the CPU awake.
The processor powers up, catches the incoming character, executes the fourth command, and the literal microsecond the bus goes idle again.
It drops right back into sub-microamp deep sleep.
That is amazing. But wait, a standard PC doesn't have an I2C port. It has USB.
Right. And this is the catch. Fastforth requires a 2-board setup. You need a secondary hardware board, basically another MSP430 launch pad sitting on your desk acting as a translator.
So this bridge board runs a script called UART IDECS.F. It talks to your computer over a standard USB to UART connection at blistering speeds, like up to 6 megabaud.
Right, and then it translates that incoming UART data into I2C to talk to the sleeping target board.
But the wild detail here, and this blew my mind when I read it, the bridge board doesn't even use the MSP430's built-in I2C hardware to do this translation.
No, it doesn't.
It bit-bangs the protocol and software. It manually toggles the GPIO pins high and low to simulate the I2C clock and data lines.
Yeah, it's doing it all manually.
I have to ask the pragmatic question here.
Sure.
Why? Why would you manually bit-bang a complex protocol when there is dedicated silicon on the chip literally designed to do it for you?
Because of errata.
Errata.
Yeah.
Hardware bugs.
Yes. This is the grim reality of embedded systems that the glossy datasheet summaries never mention. Texas Instruments' UCBX hardware I2C peripheral has notoriously complex, very well-documented hardware bugs.
Specifically regarding clock stretching and multi-master arbitration, right?
Exactly. If the target device needs an extra microsecond to process a character, it pulls the clock line low to tell the master to wait. That's clock stretching.
And the silicon peripheral often mishandles those exact edge cases, locking up the entire bus.
Yes. So the Fastforth author recognized that writing a bulletproof software bit-banging driver was vastly more reliable than fighting the silicon bugs.
By directly toggling the pins, you have absolute deterministic control over the bus state.
And because the system clock on the bridge board is running at 24 megahertz, the software I2C can easily maintain a 1 megahertz bus speed.
Which is the maximum fast mode plus specification for I2C anyway, so you're not even losing speed.
Exactly. And furthermore, it leaves the actual hardware I2C module on the chip completely free for the user's application. If you need to talk to an external temperature sensor, your hardware module is untouched and ready to go.
Okay, I get the technical logic, but I have to say, it initially sounds completely absurd, requiring a dedicated second microcontroller just to open a serial terminal to your target. Isn't that complete overkill?
If you're just blinking an LED on your desk, yes, it's total overkill. But when you look at the actual use case of the MSP430, it makes perfect sense. These chips are designed for distributed sensor networks.
Right.
The I2C protocol supports multiple devices natively. One single $13 master bridge board connected to your PC can address up to 112 sleeping target boards on the exact same 2-wire bus.
Wow. Okay, imagine a greenhouse monitoring system. You have 50 tiny sensors distributed around the room, all asleep, all drawing zero power.
Right.
And from your central PC terminal, you can direct your fourth commands to any specific node on the fly.
Exactly. The master manages the terminal negotiation using control characters. It sends hex 00 for excitate, hex FF for abort. It seamlessly manages the 0-millisecond transmission delays between all those sleeping nodes.
And what if those nodes need to store massive amounts of data locally, like logging temperature over a month?
Fastforth includes a profoundly optimized FAT32 SD card driver.
This driver is a masterpiece of optimization, by the way.
It really is. Interfacing with an SD card requires navigating complex SPI timings, initializing the card, reading the master boot record, navigating the file allocation tables, locating the cluster chains.
That's a lot of overhead.
And Fastforth manages all of that loading, reading, writing, directory traversal in exactly 3 kilobytes of memory.
To put that in perspective for the listener, standard C-based FATFS libraries often consume 15 to 20 kilobytes just for basic read and write access.
Yeah, 3 kilobytes is insane.
How does it accomplish that?
By aggressively NOP tuning the SPI bus.
NOP, meaning no operation?
Yes. Different SD card manufacturers like SanDisk or Panasonic have microscopic variations in how long they take to release the data line after a read.
Okay.
Instead of using generic bloated timer loops to wait for the card to be ready, the driver inserts exact, no operation instructions, literal one-cycle delays to perfectly align the clock edges with the specific hardware responses.
Is the absolute definition of bare metal obsession.
Truly.
So we have this beautifully orchestrated, ultra-low power embedded target. It's sleeping at sub-microamps, waking up via I2C, running massive SD cards, mixing high-level logic and assembly at 800 kilobaud.
It is an absolute masterpiece of embedded engineering.
But to actually utilize it, you have to write the code on your host PC and send it over.
Mm-hmm.
And here's where the dream collides violently with reality.
Oh, a tool chain friction.
So tool chain reality check.
Is brutal.
Because the build system is aggressively Windows-centric.
Yeah.
And deeply unapologetically antiquated.
Yeah, Fastforth completely ignores modern tools like CMake, LLVM, or Python build scripts. It relies heavily on a generic macro processor called Gima.
Gima. And for those who don't know, Gima hasn't been updated since 2002.
It is a literal relic from the era of Windows XP.
Let's trace the actual developer pipeline here, because the friction is immense. You don't just write a Forth file and send it straight to the chip.
No, you definitely don't.
You start by writing your source code in a file with a .f extension. But this file contains abstract references to hardware peripherals. Like you might write, turn on P1 OUT port 1 output.
Right, and you run that .f file through the Gima processor on your desktop.
And what does Gima do?
Gima takes a secondary file, a .pat or pattern file, which acts as a translation dictionary. It contains the hard-coded physical memory addresses for the specific chip you are using.
Okay.
Gima does a raw, offline textual substitution. It swaps out the text and spits out a completely new file, a .forth file.
So P1 OUT literally becomes the raw memory address string, like 0 by 0202.
Exactly. Then, a series of Windows batch files invokes TerraTerm, a classic, older terminal emulator, which then streams that newly generated .forth file over the serial port to the bridge board, which then finally sends it to the target.
And all of this is orchestrated from the site text editor.
Yeah, it's a very convoluted pipeline.
But I have to ask, why subject the developer to this multi-stage offline processing? Forth is supposed to be interactive. Why can't I just define P1 OUT as a constant on the chip itself and skip the 2002 preprocessor entirely?
Dictionary space. It always comes back to dictionary space.
Right, the 4 kilobyte limit.
Yes. The MSP430 family is highly fragmented. The physical memory address for port 1 output on an FR5739 is completely different from the address on an FR2355.
Ah, I see.
If you define every possible hardware register as a native Forth constant on the chip itself, you would consume massive amounts of your precious dictionary just storing hardware mappings.
And at runtime, the Forth engine would have to spend clock cycles actually looking up the address of P1 OUT every single time you used it.
Exactly. By using Gima, the heavy lifting of textual translation happens on your desktop processor.
So the microcontroller only ever sees the raw, hard-coded hexadecimal address.
Right. It costs 0 dictionary space, and it executes instantly. The mechanical rationale is completely sound.
The mechanics are sound, yes, but the cost is the total alienation of the macOS and Linux developer communities.
It really is. The author explicitly designed this around native Windows executables.
If a Linux developer or someone on a Mac wants to use Fastforth, they are looking at days of infrastructure fighting before they can even blink an LED.
Oh, absolutely. First, you have to install Wine just to run the cross-assembler, as.exe.
Then you have to abandon TerraTerm and configure Pico.com or Miniterm to handle the specific timing delays that TerraTerm was handling.
And you have to manually translate dozens of Windows.bat files into bash scripts.
And you have to somehow find or compile a working binary of Gima from 2002 for your modern Linux distro.
It's awful. And you are doing all of this while strictly adhering to the syntax quirk that every single line of code must be written in uppercase.
Uppercase only.
Yeah, no camel case, no mixed case.
Why? Why force uppercase?
Fastforth's internal find algorithm only checks uppercase ASCII values just to save a few precious bytes of case conversion logic in the kernel.
It creates an intensely hostile environment for modern teams, honestly. You have to maintain .f files, .pat files, and .forth files just to push a single update.
It really does. And this intense operational friction forces the ultimate philosophical question of the deep dive.
Right. When we look at the broader landscape of embedded forth, Fastforth stands in stark contrast to the dominant modern player, Mecrisp Stellaris.
Yes, McCrisp. McCrisp represents the modern approach to embedded forth.
It runs primarily on the ARM Cortex family, right?
Exactly. The ubiquitous chips powering almost every modern consumer device. McCrisp prioritizes portability and community above all else.
It uses standard reverse polish assembler syntax. It supports modern network stacks. It is designed to be a broadly applicable tool that you can move from project to project.
Whereas Fastforth violently rejects portability.
Violently, it chooses to achieve absolute, uncompromising excellence on the MSP430FR family and is completely intentionally useless everywhere else.
Which forces us to ask the big question. In the embedded space, does portability simply mean mediocre everywhere?
Ooh, that's a sharp way to put it.
But think about it. If your ARM framework is truly portable, it means it must rely on generic abstraction layers.
Right.
It cannot take advantage of the specific sub-microamp I2C address match wake-up of the MSP430 because that specific hardware feature doesn't exist on every single chip the framework supports.
They must resort to the lowest common denominator to work everywhere.
Exactly. Fastforth abandons portability specifically to exploit those exact hardware quirks.
And let's look at these specific advantages you get by abandoning that portability. Because beyond the HI2LO mixing in the deep sleep terminal, Fastforth completely rewrites how dictionary searches actually work.
Oh, the multi-threaded dictionary. This is fascinating.
Right, so in a standard Forth implementation, the dictionary is basically just a single, massive linked list.
Yeah.
When you type a command, the F&E routine has to linearly traverse the entire list, checking string by string until it finally finds a match. It is an ON operation.
Which gets progressively slower the larger your application becomes.
But Fastforth hashes the first character of every word and splits the dictionary into 16 independent linked lists.
Oh, that's smart.
So when you search for a word, it calculates the hash, jumps directly to one of the 16 lists, and searches only that tiny fraction of the dictionary. It literally accelerates the search speed by a factor of 4.
And it anchors the head pointers for those 16 lists inside the MSP430's FRAM.
Right, FRAM. For anyone who hasn't worked with FRAM, ferroelectric RAM, it's a total game changer.
It is. Unlike standard flash memory that needs a slow, power-hungry block erase before you can write to it, FRAM lets you write data bit by bit at full CPU speed.
But unlike standard SRAM, it doesn't lose the data when the power drops. It is incredibly fast, non-volatile memory.
And Fastforth exploits this beautifully by reserving an area called INOFO FRAM. It stores pristine copies of the system's default state in this area.
So if you're experimenting with raw assembly and, as we discussed, you accidentally mess up the IF statement and catastrophically crash the system.
Overwriting the dictionary, corrupting the return stack.
You don't have to reflash the chip. You press a specific hardware button combination, and the system executes a deep reset.
It instantly copies the clean state from INFO FRAM back into main memory, wiping away the corruption in microseconds.
It makes the iteration cycle virtually bulletproof.
It really does. But, the trade-offs for these hyper-optimized features are the hard architectural ceilings.
Right. Micris gives you massive memory headroom. Fastforth is permanently constrained by the physical reality of the MSP430.
For instance, the data stack and the return stack are hard-capped at 48 cells each.
48 cells is microscopic if you're trying to implement complex recursive algorithms or deep nested calculations.
It's tiny. And the terminal input buffer, the TIBE, is only 84 bytes. You literally cannot type a single line of code longer than 84 characters without overflowing the buffer.
And most importantly, there's absolutely zero networking capability. You are not building a Wi-Fi connected IoT smart device using Fastforth.
No, the ecosystem simply doesn't exist for it. So you, as the listener, have to perform a brutal cost-benefit analysis.
What kind of developer are you, right?
Exactly. Are you building an ultra-low-power, deeply embedded sensor node? Are you tracking soil moisture in a remote agricultural field where the battery must last 5 years and the chip spends 99% of its life asleep?
Because if that is your domain, Fastforth hands you the keys to the kingdom. You get 800 kilobaud speeds, zero overhead assembly mixing, and a sub-microamp I2C terminal.
You get a level of silicon mastery that a generic ARM framework physically cannot replicate.
But if your project requires an Ethernet stack, or a graphical display, or if you are developing on a Mac and need the safety of a massive community forum to help you out,
The friction of Fastforth will completely suffocate your development cycle. You should immediately look to MacCrisp or, honestly, just stick to C.
It's true. Fastforth is a profoundly polarizing, brilliantly engineered anomaly. We've explored the four-cycle execution of the DTC2 threading model, the seamless HI2LO gear shifting between logic and bare metal,
The brilliant exploitation of I2C hardware address matching for deep sleep.
and the agonizing reality of relying on a 2002 Windows preprocessor to make it all work.
It is a tool that demands total submission to its unique philosophy. But if you submit, it rewards you with unparalleled hardware control. And I think, honestly, that exposes a critical, perhaps uncomfortable reality about the modern embedded industry.
Which
We are rushing blindly toward generalized, cross-platform frameworks and increasingly generic, overpowered IARM chips. We throw megabytes of RAM and gigahertz of processing power at problems just to avoid dealing with the specific quirks of the silicon.
We're abstracting away the hardware completely.
Yes, we are losing the art of true hardware mastery. Fastforth proves that if a single developer is willing to completely embrace the unique constraints of a specific microcontroller, ignoring portability entirely, they can achieve performance and power profiles that outpace commercial systems by orders of magnitude.
That's a huge thought to end on.
Mm.
We spend so much time trying to engineer a massive generic cruise ship that can somehow squeeze into a tiny bottle when we could just be building the bottle out of the ship itself.
Exactly.
It completely shifts your perspective on what these tiny computers are actually capable of. Thank you all for joining us on this deep dive. Keep questioning your tool chains, keep exploring the bare metal of your hardware, and we will catch you on the next one.